All right, we're going to go into Chapter 5 and look at a section on systems of linear equations. So we've done linear equations previously in two variables and graph the lines, etc. We're going to expand upon that if we have two of those, in which many applications in the real world deal with linear models. It's supposed to be deal. And many times, two of these linear models are put together to form a system of linear equations. Now, all equations in the form ax plus by equals c are straight lines when graphed. So if you can transform that, if you remember we had y equals mx plus b, we can easily graph those with the y-intercept and the slope. Now, two such equations are called a system of linear equations, or a linear system. Now, a solution, or an answer, to a system of linear equations in two variables is the ordered pair that satisfies both equations in the system. So this is kind of what a system looks like here. And what we want to start by doing is, can you tell whether or not this point given to us, 1, 2, and 7, 6, are solutions to this system? Well, what does it mean that it satisfies both equations? Remember, this is an x and that's a y. If I were to take each of those values, plug them into each of these equations, they have to make a true statement. So, for instance, if I do 2 for the first one, 2 times 1 minus 3 times 2, is that equal to negative 4? So I took x and y, 1 and 2, put it here and here. Okay, so order of operations says I multiply first, so I get 2. 3 times 2 is 6. Is that equal to negative 4? And it is. Now, it's not just okay for it to be okay in one equation, it has to be okay in the other equation as well. So I'm going to put 1 in here and do 2 times 1 plus the y value, which is 2. Is that equal to 4? That's the question I have. So this is a 2 plus 2, and according to my books, in our base 10 system, that is equal to 4. So is 1, 2 a solution? Yes, it is. It is an answer to that system, and we'll see what does that mean here in just a second. But let's check this point. If I have the point 7, 6, I'm going to put this in the x and that in the y. So let's start with the first equation. I'm going to put a 7 here and a 6 there. So I would do 2 times 7 minus 3 times 6. Is that equal to negative 4? This gives me 14. This gives me 18. And it most certainly is equal to negative 4. Checking the second equation, putting 7 in for x and a 6 in for y, I would do 2 times 7 plus 6. Is that equal to 4? In question, well, this is 14 plus 6, and that is not equal to 4. So this does not work at all. Therefore, this is not a solution to our system. So basically, you're looking at the point that satisfies both equations. If it does, then it is what we refer to as a solution. If it does not, then it is not a solution or an answer. So when we work with systems, there's actually 3 different options that we lie into whenever we look at it graphically. So graphically, the solution of a linear system are the points or point that the lines have in common. There are 3 possibilities. Now I'm going to start with intersecting lines because most of the time this is what we're looking at, and the number of solutions will be 1. It is going to be an ordered pair. And when I have intersecting lines, what happens is that I end up having them cross at a point. The solution is the point of intersection. That's the point that satisfies both lines. Okay, so this is kind of the intersecting. I can't spell. I need a C in there. Okay, now the other type, or another type of scenario that we could have would be that we have parallel lines. Now, if you remind, parallel lines are 2 lines that never cross. So, if they have the same slope, different intercepts, but when I talk about solutions, where are the point or points that the lines have in common? And there are none. So there is not a solution for parallel lines in a linear system. And the third type is what we refer to as coinciding lines, or the exact line. I've heard it different ways. But if it is coinciding, that means it's the exact same line. They kind of represent it by 2 arrows on there like that. And it actually has infinitely many solutions to that system. And the way that we write our answer is that we look at the xy point such that it's on the line ax plus by equals c. And so that's the way you would end up having to solve or to give your answer for a coinciding line case. Okay? All right. So again, like I said, most of the time we're going to work in this intersecting line system where we have one exact point that will be our answer for our problem. Now, there are going to be 2 ways that we solve these systems, and one way is by substitution, and the other way is by the addition method. Your book refers to it as the addition method. Some of you may have heard this as elimination. I like that one better because we're eliminating out a variable when we are doing that. Now, let's start with substitution. Substitution is probably the second one that most people will use. Most of the time elimination is used, but substitution is a good way. Sometimes it's much helpful to do it than elimination. So here are the steps in order to solve a system by substitution. Number 1, we want to solve either of the equations for one variable in terms of the other. So we want to get x equal to something or y equal to something. Okay? Doesn't matter which one, just get one or the other. Now, number 2, we want to substitute that expression that we found in step 1 into the other equation. So you want to use both of the equations in this. And what's going to happen is that you're going to get an equation that only contains one variable, not both x and y's, but just an x or just a y. And when you solve that equation, you're going to get like y equals 2. Then we're going to take that answer and put it back into that we get from step 3, and we're going to put it back into one of the original equations to find the other variables. So let's see what we can do with this in this first example. Number 1, we want to solve either one of these equations for x equal or y equal, and notice that we already have that in one of it. So we have y equal, so we've done step 1. Number 2, we want to substitute the expression that this is equal to, so this is the expression it's equal to, into the other equation for that variable. So I'm going to take out a y and I'm going to put in this 2x plus 7. So I'm going to rewrite the second equation, taking out this variable that I have solved for and inputting the expression that it is equal to as 2x plus 7. We are substituting that in, and that has to equal negative 13. So what we are resulting here is an equation that only has one variable, the x's. So it's going to be a linear equation that I can solve. So I first need to do that by distributing, and we did this way back in one of the earlier chapters. Negative 3 times 2x is a 6x. Negative 3 times a positive 7 is a minus 21, equals negative 13. We're going to combine like terms, simplify as much as you can. 2x minus 6x is minus 4x, minus 21 equals negative 13. Then I'm going to add 21 to both sides. And when I do that, this goes away and I get negative 4x is equal to a positive 8. Divide by the number next to the letter, and therefore x equals negative 2. Now remember, this I actually get a value on, so we're in an intersecting line case, so I'm looking for an xy point where the x value is negative 2, but I'm not done yet. I need to find the matching y value. Now, I have originated 2 equations here that I can plug negative 2 in. You could put negative 2 right in here, times it by 2, minus 3y equals a negative 13. But I'm going to hone in right here. I have this original equation where y is equal to twice of the x value and add 7. So why not, if it's y equal, why not just plug it back in? Because you're going to kick out what it's equal to and not have to transform the equation from side to side. So here, multiply first. This gives me a negative 4 plus 7. Therefore, the y value is equal to 3. Our final answer for a system is a point, or if it's an empty set, or if it's an infinite case, we would write the line in set notation. But again, most of the time we're going to see the intersecting lines cases. Okay? All right, very good. Now I have 3x plus 2y equals 4, 2x plus y equals 1. Again, we're going to do this by substitution. Notice I don't have x equal or y equal to start off with, so I got to get one by itself. Now, if I try to start in this first equation, I want to try to get, say, x by itself. I would have to subtract the 2y and then divide everybody by 3, which creates some nasty fractions over here. So if you're doing substitution, I would really hone in on a variable that has a coefficient of 1. The reason being is because now if I want to move this 2x over, there's no number I have to divide by, creating fractions that become nasty. So I'm going to subtract 2x from both sides, and what I get is y is equal to, now you can put 1 minus 2x if you want. I'm just so used to putting the x coming first, I'm going to write that as negative 2x plus 1. Okay, so there's my y equals in step 1. Step 2 says I'm going to take this expression and plug it into the other equation for that variable. So we're going to take out the y and we're going to plug in that 2x or negative 2x plus 1. So it's going to look like this. So I'm going to rewrite the 3x plus the 2, take out the y and put in the expression from the other equation, and set that equal to 4. So all I did is replace this with the 2x, negative 2x plus 1. Let's distribute. This is solving the stuff you've already done. Everything builds, so we had to know how to solve these equations before we could get systems. Combine like terms gives me a minus x plus 2 equals a 4. I'm going to subtract 2 from both sides, and I get minus x equals a positive 2. And then I'm going to divide by a negative 1, or I can make, since I make this a positive, change the sign over there. So I actually get x to equal a negative 2. Now remember, that is part of my point. I need the y value to go along with that. Well, I can plug it in here, here, or here. It doesn't matter. I'm going to choose this one because, again, I have y equals. So if I plug that right back in for x, that means that I need to do y equals negative 2 times the negative 2 that I found from what x was equal to over here, and then we're going to add 1 to that. So negative 2 times negative 2 is 4 plus 1. Therefore, my y value is 5, making the solution to my system the point negative 2, 5, and that would be my complete answer for that system. Okay, so we had 2 lines that cross at the point negative 2, 5, and that is the answer to the system. All right, so let's talk about the addition method, or referred to also as elimination sometimes. Now, this students usually get used to this pretty quickly once we have it all kind of lined out. And the steps that we take are now 5 instead of 4. So if necessary, we want to rewrite both equations of that linear form ax plus by equals c. We want them in the same exact form stacked on top of each other, like what you see right here. Okay, now if necessary, we are going to multiply either equations or both by an appropriate non-zero number so that the sum of the x coefficients or the y coefficients is 0. We want to eliminate that. We want to get rid of it. Then we are going to add the equations together to do the elimination. Then we result in solving an equation in one variable again. And then we're going to substitute the number that we received in step 4 into any of the other equations to solve for the other variable. Okay? All right, very good. So we have 2 equations. They are in the form ax plus by equals c, so we don't have to do number 1. Number 2, we need to check that if I were to add our x's or add our y's, do they eliminate? Do they go to 0? That's what we want to look at. 3x plus 3x is 6x. That doesn't go to 0, but positive 2y minus 2y does go to 0. So there's no use for us to do step 2 and multiply the equations because we already have a sum equaling 0. So step 3 means we're going to add those equations. 3x plus 3x is 6x. That goes to 0. Bring down your equals and add these two as well. Gives me 24. Then I'm going to solve in step 4 by dividing that number, or dividing by the number next to the letter. and I get x to equal 4. Remember, that is half of my point. I now need to plug that back into one or two of the equations. It doesn't matter. I don't really want to work with that negative, so I'm actually going to plug that back in here to this original. So I'm going to go 3 times 4 plus a 2y equals a 14, and now I have that linear equation to solve. So 12 plus 2y equals 14. I'm going to subtract the 12 from both sides. 2y is equal to 2. Divide by the number next to the letter, therefore y equals 1. So the point that is my solution is the point 4, 1. Okay, so look at this next one. We are in the form ax plus by equals c. In both of those, that's nice. The x's, the y's, and the numbers line up. When I add these two equations, I get 4x plus 2x is 6x. That doesn't go to 0. 5y minus 3y is 2y. That doesn't go to 0. So we do have to engage step 2 here. We would like to multiply one or both of these equations by something so that I do get an opposite here like this that I can cancel. So what I like to do is I just kind of look at the smaller numbers of the two. Can I multiply 2 by something to get rid of that 4 very nicely? And the answer is yes. Now, can I multiply 3 by something very nicely to get 5? No, it is not, okay? So if I were to choose to eliminate the y's, this would be the case that I'd have to kind of find a common number between 3 and 5, which would be 15, to make each one of those equations like a positive 15y and then a minus 15y for them to eliminate. So we're just going to do the x's this time so I can show you. You only have to do one equation. You don't have to do both. So if I multiply this equation by 2, 2 times 2 is 4, which would match that. But we don't necessarily want to match that. We want to make sure we have the opposite of that so that we can cancel it out and make it eliminate. So what I need to do is multiply by a negative 2, excuse me, to get a negative 4 when I multiply here that I can cancel with that positive 4, okay? So here I'm going to rewrite this first equation. I'm not going to do anything to that. But if I'm going to multiply by negative 2 with this guy, then I have to multiply negative 2 all the way through. So this becomes a minus 4x. Negative 2 times a negative 3 is a positive 6y. And a negative 2 times a 7 is negative 14. And now I have my ax plus by equals c's that I can add together and eliminate the x's this time. And when I add my y's together, I get an 11y. When I add here, I get a negative 11. Divide by the number next to the letter. It's supposed to be an 11. And we get y equaling, this gives me a negative 1. Therefore, part of my answer is negative 1 on the y value. Okay, but now I have 1, 2, 3 different equations that I can use to solve for x. Doesn't matter which one that you choose. I'm just going to choose, say, this original up here and plug that y value in. So I get 4x plus 5 times a negative 1 equals 3. And now I have this linear equation to solve. So 4x, this becomes a minus 5 equals 3. I'm going to add the 5 to both sides and get 4x equals 8. Therefore, I divide by 4. Our x value is equal to 2. So the point 2, negative 1 would actually be my solution to this system of equations that I have for doing it by elimination. Okay? All right, so let's turn to the back side. Last page of this note. So let's look at a special case. Okay, now this one also has a case where we would end up having to get it into ax plus by equals c. So what I'm going to do, I'm going to go ahead and subtract that x over. And what I get is a minus x plus 4y equals an 8, along with a 5x minus 20y equals a negative 40. Okay, now notice that if I try to add the x's and add the y's, they do not eliminate, they do not go to 0. But in order for my x's to eliminate, I would like that to be a negative 5 up there. Now, in order to eliminate these, I would like this to be a 20, so I would have to multiply that by 5. So I'm going to multiply this first equation by 5. Okay, now I'm going to repeat them down here. When I distribute that through, I get minus 5x plus a 20y equals a 40. And I'm going to rewrite the second equation. And now I'm going to add them. Okay, now when I add them together, look what happens. That goes away, and this actually goes away. So I get 0 on this side, I get 0 on that side, and what I have is a case where I don't have a variable. So remember, this is one of these special cases. I believe all the times before I've done like an empty set where it's a not true statement, but here this is a true statement. That is true always. So what we have is that there are infinite amount of solutions here. Infinite solutions. This is the coinciding case where I have the same line for both of those equations, okay? So the answer is going to be all xy such that I'm on one of these lines. It doesn't matter which one that you choose. You could say you're on negative x plus 4y equals 8. Or you could put 5x minus 20 equals negative 40 here. Just put one of the lines there. It doesn't matter which one. And this would be your answer. Okay, so that's if you have a true statement. If you get a false statement, when the variables all cancel, there is no solution. Okay, no solution, and so hence you would end up having, it's a parallel line case if that is what happens. Parallel. My writing's a little sloppy. Okay. All right, very good. So that's an example of a special case. Like I said, if it ends up going to a false statement here, like 0 equals 4, then you would end up having the parallel lines case. All right, let's finish by doing a couple word problems, and setting up the equations are what's the hard part. Solving it should not necessarily be the hard part here. So if I have the sum of 3 times a number, or 3 times a first number and twice a second number is 8. If the second number is subtracted from twice the first number, the result is 3. Find the numbers. So we have 2 equations here that we want to make sure that we write each one of those equations. So let's start with the first. The sum, we're adding, of 3 times a first number, so let's call x our first and y our second number. So we have 3 times our first, so it says 3x, and twice of the second number. So I'm going to multiply twice of the second number. Is means equals 8. If the second number is subtracted from twice of the first number, if the second number is subtracted from twice of the first number, so the second number is subtracted from the first. So make sure you get the right order. We're subtracting the second number from twice of the first number, and the result is 3. So make sure that you rewrite that in an order that works. With subtraction, it can be tricky, so be careful. So these are our 2 equations, and we need to multiply or to find the answer of the 2 numbers by solving this system. So we are going to try to eliminate. I think that's the easiest of the 2. If I add these together, I don't get 0. If I add these together, I don't get 0. But if I had a nice 2 here, looking at my plus and minuses, if this could be a 2, I could eliminate. So that means in order to get that 2, I have to multiply that equation by 2. So I'm going to rewrite the first equation, and then I'm going to multiply the 2 straight through. So I get a 4x minus a 2y equals a 6 on that. And then we're going to add them together. Those go away. 3x plus 4x is 7x. 8 plus 6 is 14 when I divide by 7. Therefore, my first number x is equal to 2. And I have 1, 2, 3 unique equations to plug that 2 back into. I'm going to go ahead and just put it into this first original one. And take 3 times the 2 plus the 2y equals 8. And now solve that linear equation. So this gives me 6 plus 2y equals 8 when I subtract 6 from both sides, then I end up with 2y equals 2. And I'm going to divide both sides by 2, leaving y equaling 1. So the numbers that I want for this are the numbers 2 and 1. Now I'm not putting them in an ordered pair just because it says find the numbers. I could have let, x equal 1 and y equal 2 or whatever the case may be, but those are going to be my answers. Okay? All right, let's try the next one. The sum of two numbers is 2. If one number is subtracted from the other, the difference is 8. Again, finding the equations is the hardest. The sum of two numbers, x plus y, equals 2. If one number is subtracted from the other, their difference is 8. If one number is subtracted from the other, so I could do negative x plus y, or I could do x minus y. One is subtracted from the other, didn't specify. Their difference is 8. So if I look at this system, I'm going to go ahead and put my plus right there because look what happens when I add those two y values. They cancel. 1x plus 1x is 2x equals 10. When I divide by 2, x equals 5. And therefore, I'm going to plug that back into one of those equations. I'm just going to start with the first one and get 5 plus y equals 2. And when I subtract 5 and subtract 5, my y value is negative 3. So it just says, what are the two numbers? The two numbers have to be 5 and negative 3. And that would be my final answer for those. Okay? All right, very good. And our last little application here with systems is that talking about cost and revenue and profit. So as a reminder, when dealing with business, revenue is the money that is coming into your company. Cost is, of course, the money that is going out of your company for your expenses and stuff. And when we talk about profit, the money you get to take home in your pocket, that hopefully is positive by taking the revenue minus the cost. If it was reversed, that means you're losing money and you probably should close your business because that's not good to be losing money every month. So let's look at this example here and then we will answer kind of part C in a system form. Now, a company that manufactures running shoes has a fixed cost of $300,000. So automatically that may be like their bills, their electric, their equipment, their employee costs, etc. Now, additionally, it costs $30 to produce each pair of shoes. They are sold for $80 a pair. So this is the incoming money, revenue. Cost is going to be here and here. Okay? We need to write a cost function of producing X number of pairs. Now remember, the fixed cost of $300,000, that doesn't change. The changing part is the 30. So for part A, my cost function, hopefully you kind of recognize 30 times the number pair of shoes. So that's the changing part, $30 per pair of shoes. If I do 100, I have to do 30 times 100. Then I'm going to add on to that fixed cost of $300,000. For part B, my revenue function is, the revenue function R for selling X numbers of shoes. So here, it costs $80 per pair of shoes. So if I sell 100 of them, I'm going to take 80 times 100. So the revenue cost function is 80x. And then we need to determine the break point. Part C says, describe what that means of determining the break point. Break point means between the cost and the revenue that, your profit basically is equal to 0. That's one way to look at it. I did profit is revenue minus cost, but a break point means that what is it whenever we have cost equal to revenue? That's what they're really asking for in that piece, which is actually in a sense going to be a substitution of a system. Here I have two equations. I can substitute when that is equal to my revenue. So for part C, we're going to figure out when 30x plus 300,000 is equal to 80x. And so I have larger numbers, but that's okay. Solve it by subtracting 30x from both sides. And I get 300,000 is equal to 50x. And when I divide by the 50 from both sides, then what I get, x is equal to 6,000. Now, x was the number of shoes, right? If we come back up here, x pairs of shoes, x pairs of shoes. So x is the number of shoes, And what basically it is we need to sell 6,000 pairs of shoes to break even. Need to sell 6,000 pairs of, there's a delay here, so I'll fix that, 6,000 pairs of shoes to break even. And that's the meaning of that, okay? You wouldn't lose any money, you wouldn't gain any money. That would just be the equal cost for both, okay? All right, very good. So hopefully that's not too bad of a section. We are looking at solving those systems, and then we'll kind of also allude to some inequalities when we get into this chapter some more as well. So until next time.